Hello, everybody. So recently we were talking about the puzzles. In one of the last lectures, you saw a puzzle about knights and knaves, who were like the two brothers that you've seen in the previous puzzle. Knights were the people who always tell the truth, and knaves are the people who always lie. Whatever a knight says is always true, whatever a knave says is always a lie. But you can't really tell them apart. You could only try to figure out from their action who is a knight and who is a knave. So here is a puzzle. You meet two people from the island of knights and knaves. Let's say the first one is Arnold, second one is Bob. And you hear Arnold saying, either I'm a knave or Bob is a knight. So can you figure out from just the fact that Arnold said, either I'm a knave or Bob is a knight, whether Arnold is a knight or a knave? And would that give you enough information to know whether Bob is a knight or a knave? So let's try to solve this puzzle. Let's first convert it into the language of logic. I'm going to use two variables. Variable A, which would be true when Arnold is a knight and false when Arnold is a knave. And a variable B, which would be true when Bob is a knight and false when Bob is a knave. And what I'm after is to find out whether variable A should be true or false and whether variable B should be true or false. What we have from the puzzle is a statement, a formula, either Arnold is a knave or Bob is a knight. So we could write it as not A or B. And what we want are scenarios in which the rules of the puzzle work. So if Arnold is a knight, what he said must be true. If Arnold is a knave, what he said must be false. Let's see when this happens. So first of all, we need to expand our formula a little because we're really not interested in just whether not A or B is true or false. What we are interested is when not A or B is true and A is true at the same time, or not A or B is false and A is false at the same time. So we will use a little bit more notation, just a shortcut, syntactic sugar, the double arrow, which means if and only if. So if the first part is true, then the second must be true, and if the second part is true, the first must be true. And by the way, when you're writing the syntax trees, you would give the if and only if even lower precedence than if. So let's use this to solve the puzzle. Let's first write the syntax tree for this big formula. So if and only if, two things. One of them is that either Arnold is not a knight or Bob is a knight. And the second part is that Arnold is a knight. So let's solve it like this. Let's try to look at all the possible situations. Arnold can be a knight or a knave, Bob can be a knight or a knave, and see what happens in each of them. And the way we will do it is we will go up in our syntax tree, and for every node in the tree, for every connective, we will try to determine what value it gets in every scenario. So let's start. First of all, from the beginning, we will know what A is, what B is in every single scenario. And let's first figure out what value the not A part will take. So it will be true when A is false, and it will be false when A is true. So we just put this into the table. Then, now that we know the value of not A, we could compute the value of not A or B. We just need to look for every combination of values of A and B. For every scenario, we just need to look at the values of the two things underneath the OR, and then we'll know the value of the OR. So when A is true, that is not A is false, and B is true, we get true. When B is false, not A is false, we get false, and in other two situations, we get true. So finally, let's do the last step. And again, notice that to compute it, you only need to look at two places underneath it because you've pre-computed everything underneath it. So when would OR of not A or B have the same value as A? So when A and B are both true in the first line, they would indeed have the same value, and that value would be true. In the second scenario, when Arnold is a knight but Bob is a knave, not A or B would be false. However, A will be true, so they are different, and therefore the whole thing is false. And also, you could see that the whole thing is false whenever A is false. So what do we get out of it? We were interested in scenarios for which the rules of the puzzles, that knights tell the truth and knaves lie, are satisfied. And there is only one place, only one scenario where the rules of the puzzles are satisfied. That's the very first one, when Arnold is a knight and Bob is a knight. So great. From that one sentence that Arnold said, you now know not only that Arnold is to be trusted, but also Bob is to be trusted as well. So this method of writing a table of all possible variants of all the possible scenarios and seeing what the formulas do in each of those scenarios is very, very useful for evaluating pretty much arbitrary logic formulas. And today we are going to mostly spend time looking at how we could use that technique, the technique of truth tables, to figure out when the formulas take value true and when they take the value false. So in general, what's a truth table? It's just a table, like we just saw, which lists all possible scenarios, that is, all possible combinations of values of the propositions involved in the formula. And after that, once we have all the possible scenarios, we would take the syntax tree and we would start from the bottom, because we know what A and B and C and whatever other variables we have are in each scenario. And then for every connective, as long as we computed the connectives underneath it, or everything underneath it, we could figure out its value. And we will keep going until we have the value at the very, very top node, which will be the value of the whole formula. So let's look at not A or B. So here is the syntax tree for it. And we start by saying we know in every scenario what A is and what B is. So it's just A and B, so there are 4 possible combinations. Generally, in truth tables, if you have an extra variable, it doubles the length of your truth table. So if you have 2 variables, you have 4 lines. If you have 3 variables, you have 8 lines. And generally, you will have 2 to the n lines for n variables. OK, so now let's try to evaluate the formula. The first thing that we can do, the only thing for which we know all the values of things underneath it, is a negation in not A. So let's try to do not A. And that's really easy to do because we just take the column for A and in every cell write the opposite value. Where A is true, we write false, and where A is false, we write true. So now we know what not A is in every scenario, and moreover, for the top thing in our syntax tree, for the OR, we now have the values in every scenario of both things underneath it, so we can compute the OR. And this is what we do in the next column of the truth table, which in this particular case is our final column. So we only need to look at the 2 things underneath, the column with a B and the column with not A. And whenever both of those columns have a value false, we put in false, otherwise we put a value true. So you may notice something. You may say, wait a moment, didn't I already see that some formula which was true in the scenario when both things were true false in the scenario, false in the scenario when the first thing was true and second one false, and also true whenever the first thing was true. Wasn't it the if-then situation, the A implies B? And indeed, those two formulas have exactly the same values, exactly the same column of truth table. So we call those two formulas equivalent. And whenever you see the first combination, you could always replace it with the second and vice versa. So whenever you see A implies B, you could say, oh yeah, I know, this is the same as not A or B. And if you find implication confusing, a lot of people do because it doesn't quite match what people do in English language, very useful thing is to get rid of it by replacing A implies B for whatever A and B you have, for whatever formulas you have there, with not the first formula or the second formula. Okay, let's now run through a really long example of evaluating the formula and writing the truth table for it. If you could do this, you could do anything. So first, we start by saying no matter what scenario is, we know the values of all the variables. In this case, it's A, B, and C. And also note that we got a much longer truth table. Now we have 3 variables, A, B, and C, and therefore we have to have 8 rows to account for all the possible scenarios. Okay, so what is the first thing that we can compute? We could compute node B. It's a leftmost thing in our truth table that we can do. And in order to compute node B, the only thing we need to know is B, and we put the opposite values. Now that we have the node B, we can compute the thing above it because we also know the value of A. So A and node B, we could write the corresponding column in the truth table. And again, you only need to look at 2 things, at the value of A, which is true in the first 4 scenarios and false in the last 4 scenarios, and the value of node B, which is false in first, second, 5th, and 6th scenarios, and true otherwise. And since AND wants both of the things that it's ending to be true, the only time this happens is when A is true and not B is true, which is lines 3 and 4. Okay, let's keep going. We cannot do the OR above that AND because we don't know what's on the right side of the OR, but we can compute it. It's just negation of a C. Now that we have it, we can do the OR. And again, by this moment in time, we can forget about C and node B and A and all this stuff underneath. It's enough for us to know what the value of that AND was and what the value of that negation of that we just computed was. Okay, done with this side. We cannot do the implication yet because we don't know the right side, but we can compute it the same way, going bottom up. So we compute OR of A and C, and then we compute the negation of the thing that we got. Okay, finally we can do the thing at the top. And here's our answer for this big formula. It's true in 5 scenarios, when all things are true, or when A is false, and it's false in the remaining 3 scenarios.